Number 1 from your textbook. Let me read it out loud, and then we'll go from there. It says a tennis racket has a nylon string. If one of the strings has a diameter of 1 millimeter and is under a tension of 15 newtons, how much of it is lengthened from the original length, which is 40 centimeters? So for problem number 1, let's draw the picture. I have, well, that's not quite straight. Let's make it a straight line. So I have one nylon string. It says that the original length is 40 centimeters. Okay? It also says that the diameter of the nylon string is 1 millimeter. So really it's like, it looks like a cylinder. And the diameter from here to here is equal to 1 millimeter. All right? And then it says if we apply tension on it, a force of 15 newtons, will the string stretch and how much? Does that make sense? Now the other thing that they told us is that this was a nylon string. That's important, okay? So now, what we're talking about is modulus. So, and I thought, what we're really looking for is the comparison of the original length and the change in length. Now, if you go to page 344 in your textbooks, and this is also in your notes, there's several examples, but one example is that Young's modulus, which is a comparison of the ratio of the strain and stress, is equal to the force over the area, cross-sectional area, perpendicular to the force that's applied, all over the change in length divided by the original length. And that's the formula we need to use. And then this right here is gamma, but that's really Young's modulus. And it's a number that represents how much something will stretch, sort of. It's just a number that quantifies how much something will stretch. Compared on the, when we compare the stress and strain, and it's an elastic modulus. That means that we're going to stretch something. So a nylon cord will stretch when you apply a force to it. That's why it's on a tennis racket. They tighten up those nylon strings and it stretches, and then it makes the racket. It has an effect on the way that you hit the tennis ball, right? So if your strings are loose, the rebound of the ball is not as great because some of that energy is lost. Well, anyways, that's something else. What I need to know is what is Young's modulus for nylon? See, I have the force. The force is equal to 15 newtons, right? The area I can calculate because the area of the cross-sectional area perpendicular to the force is really just a circle, which is pi r squared. I can calculate that. That's pi, and then our radius is 1/2 of that, or sometimes it's the diameter of that divided by 4. And I'll explain that, right? Because the radius is equal to the diameter divided by 2. And so when I square this and square that, I get the diameter squared over 2 squared, which is 4. Right? So I don't know how you want to write that. You could put you could write it like this: diameter squared over 4. That's one of the formulas we have in the textbook, but that's where it comes from. And then remember that the diameter is in milliliters or millimeters, so it's got to be like pi times 0.001 squared divided by 4. Well, anyways, I have the area. And then I have the original length, which is 40 centimeters. So the original length is actually 0.4 meters. everything has to be converted to meters. Okay? And to figure out the change in length, well, that's what they're asking. How long will it be? Will it be longer? What's the change in length? All right. So based on that information, we have pretty much what we need to know. The only thing I don't know is what gamma is. Now, gamma is Young's modulus. It's like the modulus. It's like the elasticity of the material. And so on page, I'm trying to find the page number, but this was also in your notes, but it's in your textbook. There's a list of all these different moduli. That's the plural for modulus. And for nylon, it's on page 314. So on page 314, there's a chart that has all the different moduli: Young's modulus, shear modulus, and bulk modulus. And then for nylon, we find that it's 5 times 10 to the 9. And remember that for dimensional analysis, this is newtons per meter squared. Okay? So I have 1, 2, 3, 4, 5 variables. I have numbers for 4 of the 5, and they're asking about the 5th one. So I just got to plug in the numbers and solve. Okay? So let's do that on the next slide. So remember, this is what we're starting with, delta. So now if I were to do this, what I want is I have to find the area. I said that that would be pi times the diameter, which is 0.001, and I have to square that over 4. If I plug that in my calculator, which I'm going to do in just a second, I'll find out that that is actually 7.85 times 10 to the negative 7. Okay? And that would be meters squared because it's an area. So let's just verify that and make sure Mr. Adams has his notes written down. But I want to, so if you have your calculator, pull your calculators out, turn them on, make sure you know how to plug this in your calculators. So what I end up with is pi, pi times 0.001 squared divided by 4. Yeah, 0.78, and that, remember, e to the negative 7 is the same as 10 minus 10 to the negative 7. That looks a little, I could do a little bit better job of how I write that in. It just didn't quite fit on my board there. So that's the area. We said that the force was just 15 newtons. We said that the original length was actually 0.4 meters. We said that gamma was, what was it? For nylon, it was 5 times 10 to the 9th. So it was 5.0 times 10 to the 9th. And that's 4 of the 5, right? And then I'm solving for delta L. So let's plug these numbers in and see what we get. So I've got 5 times 10 to the 9th is equal to 15 divided by 7.85 times 10 to the negative 7. That's all this stuff here. Let me change some colors around. And then that's going to go over delta L over L naught, which is going to be 0.4 meters. Okay? Does that make sense so far? Mm-hmm. All right. Now here's a tricky thing. There's lots of ways you could do this. I need to start moving some stuff around and get delta L by itself. So this is technically like a proportion. In other words, I can multiply this and multiply this and set them equal to one another. So what I'm going to do is I'm going to say 5.0 times 10 to the 9th times the quantity delta L all over 0.4 is equal to 1 times this stuff, 15 over 785 times 10 to the negative 7. It looks messier than what it really is. So if I take 5 e to the 9 and divide that by 0.4, guess what I get? 1.25 e to the 10. So I get 1.25 times 10 to the 10 times delta L. Now I'm gonna simplify this number by taking 15 and dividing it by 7.85 times 10 to the, what was it, negative 7? Is that what that was? Yes, Mr. Adams? All right, so that's a really big number, isn't it? Let me make sure that was the right number. Yep, all right. So that number is 19108.280.25. Was it 1908108 280.25? What do I got to do to get delta L by itself? I'm going to divide both sides by 1.25 times 10 to the 10th, right? Those mean the same thing, right? I just wanted to show you what they mean. This is how I'm going to plug it in the calculator. So I'm going to take that number that I have, and I'm going to divide it now by 1.25 e to the 10. And I get 0.0015. So I get 0.0015, and that is the change in length, right? In meters. Now what does that mean? Well, what that means is, no. Yeah, hold on one second. When you apply 15 newtons, what it does is this will stretch 0.0015 meters. Does that make sense? Okay.